The mole is the foundation for most of the calculations we do in general chemistry, so it's really important. To give you an idea of why, let's say you were in a lab and I said, measure out 12 grams of carbon. That wouldn't be a problem. And then react it with an equal number of molecules of hydrogen. So you're like, okay, well, let's see. How do you relate grams to molecules? How do you know how many molecules or how many atoms of carbon are in 12 grams? That's where the mole comes in. So what chemists needed is a conversion factor that relates the number of atoms in a certain mass or weight of sample. Make sure you understand that a mole is just a number of objects. Just like a dozen is 12 objects, a mole is 6.02 times 10 to the 23rd objects. So anything you can count, like 1, 2, 3, 4, you can have a mole of. But it'd be kind of silly to have a mole of shoes, for example, because we never had that many we're dealing with. Whereas with atoms and molecules are so small that 1 mole of atoms or 1 mole of molecules is just a little sprinkle in your hand. So that's the type of unit that chemists need to deal with. A mole is also called Avogadro's number. Since a mole is a counting number, it's only useful when you're talking about particles. Okay, and in chemistry, what are the particles we might deal with? Atoms, molecules, ions, formula units. Okay, and now I'm probably really just beating a dead horse, but just to kind of let you see, you can have a mole of anything, whether it be an atom, a molecule, anything that you can count. And this, which is an ionic compound, because it has a metal in it, is called, instead of being called a molecule, is actually called a formula unit. You can also count ions, so you could have a mole of ions. This slide is just for perspective. If you had a mole of soda cans, for example, that would cover the surface of the entire Earth and extend up into the sky over 200 miles. So that gives you an idea of how very, very, very small atoms and molecules are. And just to let you know who came up with that kind of obscure value, 6.02 times 10 to the 23rd, where's that coming from? Well, whenever scientists try to standardize a value, they obtain something that they measure very precisely and then refer to. So what they did is they took 12 grams, exactly 12 grams, of carbon-12 isotope, which is the most abundant isotope of carbon, and determined exactly how many atoms were in that 12-gram sample of carbon-12. And as it turns out, 6.022 times 10 to the 23rd is exactly how many atoms of carbon-12 are in a 12-gram sample. And so that's the standard for 1 mole. And so because of that, we can say 1 mole of carbon-12 equals 6.02 times 10 to the 23rd carbon atoms. So here's the conversion factor to remember, commit to memory. 1 mole of any type of atom or molecule or ion is equal to 6.022 times 10 to the 23rd of that atom. And that is the conversion factor we will use in converting from any type of particle, let's say atoms, to moles. Why do we need moles? Why don't we just write down how many atoms we have? Because we'd have crazy numbers, like 3 times 10 to the 526 atoms. So the mole gives us some more just kind of easy to handle numbers. As all conversion factors, when we do dimensional analysis, we arrange our equivalent or conversion factor in a ratio form. And depending on the units you start with and the units you want to end up with, the particles will be on top or the bottom, and similarly, moles will be on the bottom or top. So here's an example. Here's a simple example. Look at the question, remember the rules or the process we use to do dimensional analysis. You start with a given information, which is 2 moles of lithium. You are still having to pay attention to sig figs at this point. And the problem asks us to get to atoms. Well, remember our rules. Whatever units are in the given information belong in the denominator of our conversion factor. So we know there's 1 mole. The number 1 always goes in front of mole. And on top, the units we're trying to get to, atoms. So 2 times Avogadro's number, 1.2 times 10 to the 24th. Count sig figs. The answer should have 3 sig figs, and it does. Let's flip that around and go backwards. How many moles are in this many atoms of carbon? Start with the given information, 6.02 times 10 to the 23rd. Atoms are our given units, so make sure that your conversion factor has atoms in the denominator so they cancel. And in this case, you see we have a division problem. So we have 6.02 times 10 to the 23rd divided by 6.02 times 10 to the 23rd. So we have exactly 1 mole of carbon. Again, pay attention to significant figures. See if you can work these 2 problems out on your own. So put the video on pause. See if you can work them out, and I will give you the answer on the next slide. Here are the answers. Let's see how we would go about working it out. Starting with 0.500 moles of aluminum, I set up my dimensional analysis. I know that I want moles on the bottom, and I'm trying to get to atoms. Those are the units that go in the numerator. I know 1 always goes in front of mole. How many atoms are there in a mole? There are 6.02 times 10 to the 23rd atoms in 1 mole. You now have a multiplication problem, 0.5 times Avogadro's number. Your correct answer is C. How many moles of sulfur are there in this many sulfur atoms? I'm going to start with my given information. Atoms are my units that I begin with. I have to make sure that my conversion factor has atoms in the denominator so that those units cancel out. I'm trying to get to moles, so those units go in the numerator. The number 1 goes in front of mole. And 6.02 times 10 to the 23rd atoms. Atoms cancels, and of course this is now a division problem. You have 1.8 times 10 to the 24th times 1 in your numerator, 6.02 times 10 to the 23rd in the denominator, and the correct answer is B. So far we've converted between the number of particles and moles using Avogadro's number as a conversion factor. Now this gets perhaps a bit trickier. We're going to learn to convert between the number of moles and the mass of a sample, which is actually a bit more useful for a chemist because mass is what the chemists can weigh and measure in the lab. The convenient thing is our conversion factor for going from mass to moles is simply the average mass that you see on the periodic table for each element. So if you look at a particular element, let's say silver, look at the bottom of the silver symbol and you will see that average atomic mass. That mass given is the mass for 1 mole of that element. Okay? So another name, another way to express the mass for 1 mole of something is called molar mass. That's what we'll be using as a conversion factor going from mass to mole. They're the molar mass that we find in the periodic table. If you're talking about an individual atom or element, you simply use the mass, average atomic mass in the periodic table. But what if you're talking about molecule or compound that has more than one atom in it? So, for example, calcium phosphate has 3 calcium, has 2 phosphorus, and it has 2 times 4 or 8 oxygen. How do you get the molar mass of this compound? You simply add up the molar masses of all of the individual atoms that make up that compound. So there are 3 calcium, so 3 times, look in the periodic table on calcium, you'll see that the average atomic mass is 40.078. So the mass of calcium and calcium phosphate is 120.234 grams. There are 2 phosphorus, so the contribution of phosphorus to the mass of calcium phosphate is 61.948. And the mass of oxygen in calcium phosphate is 128. Now, I haven't shown the units on the individual atoms, and I should have. Every time, this is very important, that you're calculating any type of molar mass, remember that the units are grams per mole. That's how many grams of the substance there is in 1 mole of it. Grams per mole. Very important. So to find the entire molar mass of calcium phosphate, add all of these individual atom masses up, and you get that the molar mass of calcium phosphate is 310.18. One other very important thing that I want to point out to you is when you are recording molar masses from the periodic table, make sure that you record the number from the periodic table with either all of the digits that it shows or at a minimum with 2 digits to the right of the decimal point. Okay, I don't want you rounding molar masses to whole numbers. Okay, you lose a lot of the precision when you do that. Go ahead, give this a try. Make sure you can do it on your own. What is the molar mass of tin 2-bromide? We haven't learned how to name really, but I'm using the right names. So remember when you're recording molar masses to go to the hundredths place or 2 digits to the right of the decimal, and make sure you have the right units. So I would turn off this video for a minute, make sure you can do it on your own. If you haven't already printed out a copy of the periodic table to carry around with you, that'd probably be a really handy thing to do. Did you get 278.51 grams per mole? If you did it correctly. Now that we know how to find molar mass, we are going to use molar mass as our conversion factor when we're doing dimensional analysis that goes from grams to moles or moles to grams. Okay, so molar mass is only used for these type of conversions. Okay, remember when you're converting between atoms or molecules and moles, you use Avogadro's number. So only when you see grams do you want to use molar mass. So, for example, if we have 12.01 grams of carbon, and that's the average atomic mass for all of the carbon isotopes that you will see in the periodic table, that means we have 1 mole of carbon. And so the conversion factors we could use, depending on the units we're trying to cancel, would be here. Here's a simple example to start with. How many grams of aluminum are in 3 moles of aluminum? Now, the first thing you should tell yourself is you have grams here, and that should alert you that you need to use molar mass as your conversion factor. You would look up the molar mass for aluminum on the periodic table, and here is your conversion factor. So let's go ahead and set up our dimensional analysis. The problem told us we started with 3 moles of aluminum. We know that our molar mass for aluminum from the periodic table is 27.0 grams. We want to make sure we put the 1 mole in the denominator of the conversion factor so that moles cancels out. And we end up with 81.0 grams of aluminum. Now the calculations start getting a little trickier. Let's say that we want to go from grams of an atom or molecule to the number of atom or molecules. The first thing to point out, and I would make a big note of it, you cannot go directly from grams of a substance to the number of atoms. You must always go through moles. Okay? So this ends up being a 2-step conversion. Okay? So moles is in the middle of everything. If moles was not mentioned in a question or a problem you're given, that means that that will be the first calculation you have, is to find out how many moles you have. In this case, if we're starting with grams or mass, the first thing we do, of course, is to convert from mass to moles using the molar mass. Once you have moles, then you can convert from moles to the number of particles using Avogadro's number. So here's a brief concept map of a 2-step calculation. So say we have grams, moles, and particles. Remember that particles would be atoms or molecules or ions, okay, something you can count. So again, you cannot go directly from grams to particles or particles to grams. Can't happen, okay? You go from grams to moles using molar mass. You go from moles to particles or back and forth using Avogadro's number. So you might want to start making a little concept map for yourself. Here's a fancier looking mole map. We call it mole map. Now we have not learned about liters of a gas, so you can ignore this branch of the mole map so far. But we have learned about converting between particles, moles, and grams. I want to point out a couple of memory tricks for you that have come in handy for me. If the given information in a problem is mole, you will always end up multiplying. Get it? Mole. If it's mole, you multiply. Okay. If the given information is not mole, so if it's particles or grams, for instance, you're going to end up dividing. Just kind of a little tip. Here's a sample 2-step calculation. How many atoms of copper are present in 35.4 grams of copper? The first thing you should notice are that moles are not mentioned. What did I say to do if moles are not mentioned in the problem statement? The first calculation you're going to have to do is to go to moles. Moles is in the middle of everything. As always, start with the given information. The units are grams. Anytime grams are involved, you need the molar mass from the periodic table. The molar mass of copper is 63.5 grams. Remember that 1 always goes in front of mole. Your grams of copper now cancels. You can either get an answer to that, which would have units of moles, and then do a second calculation, or you can do it kind of in a run-on fashion like I've done. So at this point, your units would be moles of copper. The question asks us to get atoms of copper. So in order to go from moles to atoms, we use Avogadro's number as a conversion factor. We must have the units moles in the denominator so they cancel. And we know there are 6.02 times 10 to the 23rd atoms in 1 mole. So what do we have when we have this calculation? Multiply everything together in the numerator. It's 35.4 times 1 times 6.02 times 10 to the 23rd. And then multiply everything together in the denominator, 63.5 times 1. I would strongly suggest getting your calculator out now and making sure that you get this same answer that I did, 3.36 times 10 to the 23rd, because as I mentioned in class, when you end up multiplying and dividing in a number of steps, many students enter it wrong into their calculator. And here is a really good problem for you to work out. So turn off the video, see if you can do it, and then I will work it for you on the next slide. The steps that you need to go through to solve this is you can look at your mole map, which I think is usually helpful, and the given information is molecules, so you're trying to go from molecules to mass. Now remember, if moles is not mentioned in a problem, that's the first calculation. Moles is in the middle of everything. So if you look at your mole map, you're going from molecules to moles to grams, which is mass, of course. So start with our given information. Notice that it has 3 sig figs because you are going to have to report your answer with the right number of sig figs. In converting from molecules to moles, we use Avogadro's number, so our first conversion factor. That cancels out the molecules. And if we were to stop after this first calculation, our units would be moles, but the problem's asking us for mass. And so we have to convert from moles to mass, which is grams. Anytime you see grams involved in a conversion, you need the molar mass of the compound. To find the molar mass of glucose, you literally look up the molar mass of every atom involved. So looking at that formula, we have 6 carbon atoms, each of which have a mass of 12.01 grams per mole. Glucose has 12 hydrogens, each have a mass of 1.01 grams per mole, and 6 oxygen. Now, if you round it correctly, you'll find that each oxygen atom has a molar mass of 16.00 grams per mole. So when you add all those together, you will find out that the molar mass of glucose is exactly 180. When you complete this calculation, I'm hoping you got 359 grams. That is the correct number of sig figures to have also. That's it for the lecture on moles.